In this discussion video, we'll do an example where we show two graphs intersect. So this is from worksheet 4, problem number 5, and it says show that the graphs of f of x equals sine of pi x over 2 plus 4x squared and g of x equals x to the third over 2 minus 10 intersect at least once. So I want to first give you 2 minutes to think about how you'd get started. It's not going to be enough time to finish the problem most likely. Just think about the key ideas and how you'd begin. 4, 3, 2, 1. Pause it for 2 minutes. Think about how you'd get started and then try to make some progress from there. Alrighty, so hopefully you did that. Hopefully paused it for 2 minutes to think about getting started and what the key ideas are. Let's talk about it together now. So my graphs would intersect when f of x equals g of x. I would set those equations equal to each other. So f of x is sine of pi x over 2 plus 4x squared, and I'm setting that equal to g of x, x to the third over 2 minus 10. And the next step, I think, takes a little bit of thought, but I can rearrange this so that the constant term is by itself on one side, and I have some function on the other side. So I'm going to move the 10 over to the left, and that's going to be equal to x to the third over 2, and then subtracting 4x squared, and subtracting that sine term, minus sine of pi x over 2. Because what I'm trying to do now is, if I call this whole function on the right-hand side h of x, I'm trying to show that h of x equals 10 at least one time. Somewhere it's going to be equal to 10. Now that we've set it up, I think it's a little bit easier now from how we had it before. I want you to pause the video for 3 minutes and see if you can proceed from here. 4, 3, 2, 1. Pause it for 3 minutes and see if you can try it from here and figure out, well, what is the key idea that we use and solve this problem? Alrighty, so hopefully you did that. Hopefully you paused it for another 3 minutes or so to try this. So if I'm trying to show that a function like this equals some particular output, one strategy is to use IVT, the Intermediate Value Theorem. So let's recall what that says. If I'm going to use the function h, because that's what I'm calling my function here. If h is continuous on a closed interval from a to b, and n is a number that is strictly between f of a and f of b, then there is a number c which is in the open interval from a to b such that h of c is equal to n. So in our lecture videos, we drew a picture of this to help us visualize, well, what is this saying and why is it true? So our goal in this problem is that we want to find these numbers a and b such that when I plug one of these numbers into h, like a, I get something out that is less than 10. And when I plug in the other number, b, into h, I get something that's bigger than 10. Because the intermediate value theorem will say, well, as long as my function is continuous the whole way, then somewhere in the middle between a and b, the y value is going to have to be exactly 10. All right, so let's plug in some values into h. So usually we try to plug in some x values that are kind of nice and easy to simplify first. And with this function, I would say 0 is going to be an easy one to simplify. If I plug that in, I will get 0 minus sine of 0, and sine of 0 is also 0. So overall, this is 0, and that's less than 10. So that's useful. I just now need to plug in something that'll give me an output that's bigger than 10. Okay, so let's see, I'll have h of, let's think about what to plug in. Maybe let me just try 1. If I plug that in, I'll get 1/2 first, and then minus 4 minus sine of pi over 2. And sine of pi over 2, that will be equal to 1. So that is 1. And then a half minus 4 minus 1. That is going to be negative 4.5. Okay, so that is still less than 10. In fact, we made it even smaller. I need to plug in something that's going to end up with the output being a lot bigger. I want it to be bigger than 10. And seeing that I have this x to the third term and this x squared term, I know that the bigger power term is going to dominate growth as x gets larger. So let's just plug in something that is a lot bigger. Let's do something much bigger. So if I plug in a number like 10 into our function, 10 is going to be nice because it's easy to work out powers of it. I'll get 10 cubed, which is 1,000 over 2, and then minus 4 times 100, minus sine of 10 pi over 2, which is 5 pi. And sine of 5 pi, that's going to be 0. And then we have 500 minus 400, which is 100, and that is definitely greater than 10. So at this point, we've achieved our goal. We've found a number that I can plug in to get an output that's less than 10, and a number I can plug in to get an output that's bigger than 10. In fact, I have two inputs, 0 and 1, that I can plug in to get the output to be less than 10. So let's just say I could use 0 and 10, or I could use 1 and 10. Maybe let me just use 1 and 10, just because that's a little bit narrower of an interval, so it lets me be a little bit more precise about where the root is. But now I state my conclusion, that h of x, my function, is continuous everywhere, because it involves a trig function and a polynomial being, in this case, they're being subtracted, and polynomials and trig functions, well, sine at least, are continuous everywhere. And there's a theorem that says when you subtract two continuous functions, that'll be continuous. Okay, so our function h is continuous everywhere, so it's continuous. Ooh, let's write that better. So it's continuous on the interval from 1 to 10. And then since h of 1 is less than 10, and when I plug in 10 into it, h of 10 is greater than 10 by IVT, the Intermediate Value Theorem, there is a number. There is a number, c, in the open interval from 1 to 10, such that h of c will be equal to 10. All right, and that's exactly what I wanted to show. Thus, f and g, our two original functions, will intersect at least once, because we've just shown that they will intersect at this number c.